This meeting is being recorded.
Good afternoon, everyone. Welcome to the final day of the FDP. I hope that all the participants are enthusiastic and ready to maximize their learning from today's sessions as it is the last day. So, to begin with, we have an insightful session titled Hybrid Classical Quantum Models. It gives me a great pleasure to introduce today's esteemed speaker for this session, Dr. Chinta Someswara is an accomplished academician, researcher, and industry expert with an impressive career spanning over 16 years in software development, academia, and research. Dr. Rao holds a PhD in computer science engineering from JNTU Hyderabad, along with an MTech in computer science and technology and MSc from Andhra University. He has made significant contributions across various domains, including generative AI, machine learning, information retrieval, data mining, and data science. His remarkable work comprises over 80 publications in prestigious international and national journals and conferences, such as IEEE and other conferences. Dr. Rao is also a proud holder of 6 Indian patents in genetics, agriculture, and data transformation. Dr. Rao's expertise has attracted substantial funding for research, with UGC major AICTE supporting 2 of his government sponsored projects. His impactful contributions span diverse applications, including human activity recognition, land cover classification, fake news detection, brain tumor detection, breast cancer prediction, and many more. Currently, Dr. Rao serves as a senior software developer at Yanthraa Information Systems, where he leads initiatives in data science, machine learning, and advanced analytics. He is dedicated to building high performing teams and designing cutting edge data driven solutions that drive business transformation. In addition to his professional achievements, Dr. Rao actively contributes to the scientific community, serving as a reviewer for esteemed journals like Supercomputing and Annals of Data Science. He is also deeply involved in exploring advancements in AI technologies, including OpenAI's and GPT-4, to remain at the forefront of innovation. We are honored to have you, sir. Thank you for accepting our invitation and having here today.
Yeah, thank you, Dr. Silpa Madam, for your wonderful introduction about me and all. Yeah.
Can you
Okay.
switch on your video, sir?
Yes. Yeah. A little bit blur in my maybe some issue with my camera actually. Yeah.
Oh.
Yes. Okay. Yes. Yeah. Good afternoon, one and all. Yeah. Yeah. Can I start, madam?
Yes, sir. You can
Yeah.
share your screen, sir.
Yes. Yes. I'll share my presentation in my screen. Yeah. 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 Today, I am going to give an idea about hybrid classical quantum models. Yeah, coming to the introduction, we all know nowadays AI is a buzzword. With or without knowing, we all are using our mobiles, laptops, wherever. We are using the AI, especially machine learning. This machine learning has transformed the industries, right? Yeah, even though we are using GPUs, TPUs, and etc. To improve the performance and scalability, yeah, still some lag is there in terms of efficiency, performance, whatever. So to fulfill that gap, that lag, we need a something. Maybe that lag will be achieved or overcome by using quantum computing. Yeah, this quantum computing is one of the solution that leveraging principles of quantum mechanics. Yeah, maybe this talk will give you some idea about this quantum computing and how the classical models we are trying to use in quantum computing. And then what is quantum computing, how we can implement in some Python or something, some other technology like that. I'm going to tell you these all things. Coming to, first of all, I start with the classical machine learning, foundations and challenges. We all know that what is machine learning, right? In generally, machine learning classified are categorized into, I'm talking about broadly. First one is the supervised learning. Second one is unsupervised learning. We all know that what is supervised learning and what is unsupervised learning. Here in the supervised learning algorithms, we have to train the algorithm or a machine with labeled data. That supervised learning further classified into regression and classification. Data of type continuous will use the regression. Data of type categorical will use the classification. I'm not interested to go to the in details about this particular regression, classification, all the things, because you all are having the idea about that. Okay, these are the things in supervised learning. In the supervised learning, we have a known data, but by using the data, we are going to train the model. After that, we have to perform some operations. Maybe it may be a continuous or it may be a categorical. Coming to the unsupervised learning, we don't know about the data. So in that case, I mean, we have a data that's unstructured or unlabeled. In that case, we will try to use the unsupervised learning. Most of the things, I mean, here we are in this unsupervised learning, clustering and dimensionality reduction will come. In the clustering, again, we have different techniques. Right. One of the simple and very famous technique is K-means. Right. And one more learning comes under this particular machine learning is a reinforcement learning. Now, instead of two classifications, I mean supervised and unsupervised, reinforcement is also added now. Right. Nowadays, we all know the reinforcement learning, because agents learning via rewards in an environment. That's called a Q learning. In most of the cases, in the Q learning, we are going to use the Bellman's equation. By using that Bellman's equation, we have to provide the rewards, and based on that rewards, we are going to train the agent about the environment. This is a small introduction about machine learning. Coming to challenges, here we have large scale data, optimization problems, and high dimensionality. These are the computational challenges. Even though we are using GPUs to train the model like GPT, it will take weeks or hundreds of GPUs, right? Even though we are using the GPUs and TPUs, it will take weeks to train the model because of this large volume of data. Another challenge is optimization problem. In this, finding global optima in non-convex functions can be slow. I mean, optimization is very, very important. In every problem, this optimization is very, very important. This is also one of the computational challenge. Another one is the high dimensionality. Right. Nowadays, this number of features will increase automatically. That is one of the challenge to handle. Right. These are the computational challenges about the data. To overcome this, we will use the quantum computing. That means that is one of the solution to this particular challenges. Right. Coming to quantum computing. Okay. Here we have three principles. I mean quantum principles. We called as a quantum principles. First one is the superposition, entanglement, and quantum interference. Coming to the superposition, here a qubit exists in a combination of 0 and 1 until measured. What is qubit? I'll get back to this slide. Now I'll go for this qubit. What is qubit? See, this qubit is a qubit. It is also called a quantum bit. Right. In this, quantum computing, Mainly it is related to the quantum mechanics. See, a qubit is also called a quantum bit, is the basic unit of information in quantum computing. It is a qubit is a basic unit of information in quantum computing. Right? What it is? What is qubit? What it is? How it's created? How it's represented? How it's different from a bit? I mean that binary digit, and how it's used. See, it's a qubit is a quantum bit. It is the basic unit of information in quantum computing. Yeah, a qubit is a two-state quantum mechanical system that can represent a 0 and 1 or any proportion of 0 and 1. That's called a qubit, a two-state quantum mechanical system. Yeah, how it's created? Qubits are created by manipulating and measuring quantum particles. See, it is one of the important things we need to remember how it's created. It's a measuring quantum particles such as electrons, photons, ions, or superconducting circuits. Okay. Right, we all know that bit, right? In that bit 0 and 1, in general, we are represented with a charge like that. Here, how it's created? Qubits are created by manipulating and measuring quantum particles such as electrons, photons, ions, or superconducting circuits. Okay, coming to how it's created. The state of a qubit is described by a quantum state vector, which is a two-dimensional column vector of unit now. How it is different from a bit, I mean our binary digit. A qubit is similar to bit, binary digit in classical computing, but behaves differently because it is from a particles, I mean quantum particles or electronics, because of quantum properties. Okay, how it's used? Qubits are quantum mechanical phenomena such as superposition, which allows quantum algorithms to process information faster than classical systems. How it is used, right? Because of this information faster than classical systems. It's a 100x or sometimes 1000x faster than the classical systems. I'll show you that example as well. Now get back to our previous slide, quantum principles. In these quantum principles, we have three components. First one is the superposition. Second one is the entanglement. Third one is the quantum interference. In the superposition, a qubit is a quantum bit, exists in a combination of 0 and 1 until measured. And coming to the entanglement, it is a correlation between qubits. In general, 0 and 1. That correlation will be handled by this entanglement, correlation between qubits, allowing joint states. And quantum interference, leveraging wave-like properties to amplify correct outcomes. It will try to rectify the errors, leveraging wave-like properties to amplify correct outcomes. Okay, we'll get back to this hardware and all. These are the three components that are there in the quantum principle: superposition, entanglement, quantum interference. Right. This is about qubit. Coming to C, here, this is a 5-step or 6-step quantum computing process. See, here you want to determine the parity, even or odd, of a binary number using a quantum circuit. Here, first one in generally qubits. Understand the quantum bits. A classical bit can be 0 or 1. A qubit, it's a superposition, can be in a combination of 0 and 1 simultaneously. And then we are going to initialize the quantum system. Start with 2 qubits. First one is the Q0 and Q1. Second one is the Q1. Initialize in the state 0. And then second in this, add 1 classical bit to store the result of a measurement. Here we start with the 2 qubits and 1 classical bit. That is that is used to store the result of a measurement. And coming to here, these two steps are important, very, very important. in this first step, we are going to use the head mod gate. In this step, we are going to use the C0 gate. In this apply a quantum gate, here we are going to use the head mod gate on Q0 to create superposition. After applying H, that means head mod gate, Q0 is in state of 0 plus 1 by root 2. Okay, this is about this particular head mod gate. Coming to encode the parity problem. Here, to calculate parity, use a C0 gate. Yeah, in this first one, superposition, we are using the head mod gate. Whereas coming to calculate the parity, we are going to use the C0 gate. See, here to control qubit is Q0 and the target qubit is Q1. I mean, here Q0 is the control qubit is Q0 and Q1 is the target qubit. If Q0 is 1, then C0 gate flips the Q1. If there is a 1 in Q0, then C0 gate flips the Q1. Now Q1 holds information about the parity. Okay, this is about computing. I mean, it's a simple example for quantum computing process. Okay, we'll take some other examples as well. Measure the output, measure Q1, which collapses its quantum state to either 0 or 1. I mean, it measure the output. It is 0, then it is called a even parity. It is 1, then it is called odd parity. Here, interpretation. The measurement result is stored in the classical bit. Here, see, we mentioned here, step 2. If the result is 0, binary number has even parity. If the result is 1, the binary number has odd parity. This is a simple quantum computing process. Now, why quantum ML? Quantum machine learning, right? That is our topic. I mean, hybrid classical models, or hybrid quantum models, right? Here, first one is the speed. Second one is high dimensional data. Third one is natural optimization, right? Speed, that is one of the key factor here. To increase the speed, okay, I'll show you one example here. I'll stop. Yeah, I want to share. No, 1 minute. More sharing option, yes. Madam, can I stop the presentation and go back to my original screen? Is it okay?
Yes, sir. Yes,
Yeah,
sir.
Okay, thank you. Yes. Yeah. See, my screen is visible, right?
Yes, sir.
Yeah. See, I'm talking about that speed. See, yeah, I think a few days back, this news came. Meet below our state of the art quantum chip. Yeah, this is from Google. Okay. Yeah. See, this is I'm talking about speed. See, Willow's performance. This one. Willow's performance on this benchmark is astonishing. It's performed a computation in under 5 minutes that will take one of today's fastest supercomputers. I mean, these guys designed a chip that chip solved this problem. For the supercomputer, it will take 10 septillion years. Okay, but coming to the quantum computing chip, it minutes, in under 5 minutes. It solved that one in under 5 minutes. That's the thing here, right? Yeah, get back to here, our presentation. Speed. See, algorithms like some algorithm here for the search problem. One of the why quantum ML. speed. This is one of the thing we need to consider. Speed, right? High dimensional data. Quantum states represent data more compactly. High dimensional data. Speed, high dimensional data, right? Number of features will increase automatically. That will increase our computational time will increase. We need a high efficient models, right? These all things we need to consider. Yeah, some of you guys having the real time knowledge, right? While we are using even GPUs or TPUs, it will take time to handle these particular things. High dimensional data. That is one of the important key factor here. Another is the natural optimization, right? Optimization is one of the key factor, right? Variational circuits align well with classical ML optimization problems. So due to these three things, we need the quantum ML, right? Okay, coming to my screen is visible, right? That my PPT.
Yes, sir.
Yeah,
So,
thank you.
no, sir, PPT is not visible. You have to again open the PPT.
Yeah, sure. Okay. Stop the presentation. Yeah.
No, directly you can open your PPT.
Now it's visible. You are about to stop. Yeah.
Yeah.
Okay. Okay. Yeah. Yeah. Hybrid classical quantum models, right? Here, hybrid classical quantum models combine, strength of, classical model having some strengths, quantum computing having some strength. We have to combine both of them. That's called a hybrid classical quantum models, right? Here, these models are designed to address current limitations of hardware. That's called a noise scalability, while leveraging the advantages, computational advantages that quantum systems can provide for specific tasks, right? Here we are going to combine both the strengths of classical and quantum computing. Coming to, what is the motivation here? See, motivation of this hybrid models, right? First one is the classical strengths. Second one is the quantum strengths. We need to combine, right? Quantum strengths. It's a high dimensional. It is going to solve the high dimensional problems, faster optimization and parallel processing. That's the main strengths of quantum computing. Whereas coming to classical models, established algorithms, scalability, it is already having the proved algorithms. So both the things we are going to combine here. Yeah, hybrid models aim to bridge the gap between current noisy intermediate scale quantum devices and fully, error corrected quantum computers of the future. Yeah, now how hybrid models will work. Here, see, in the hybrid model, we have these steps: data preparation, quantum computation, classical post processing, and iteration. Yeah, right. In the hybrid model, we have 4 phases. First one is the data preparation. Second one is the quantum computation. Third one is the classical post processing. Fourth one is the iteration. Whereas coming to the data preparation, we all know in generally for every model, data plays the key role, right? It's very, very important. Here, the classical processor prepares the input data, right? The classical processor prepares the input data and sends it to the quantum computer in a suitable form, right? First of all, we have a classical processor. That classical processor prepares the input data and send it to the quantum computer in a suitable form. Example, quantum states, because that will accept by the quantum computing machine. So that's the reason to prepare the input, I mean pre-process it and send it to the quantum computer in a suitable form. Example, quantum states. Whereas coming to the second phase. Okay. Quantum computation. Here, this particular quantum computation, in generally in this, we are going to perform a task. Right? The quantum computer performs specific tasks such as optimization or kernel evolutions. This is one of the important thing here. That means core mechanism, quantum computation. In this, quantum computer performs specific tasks such as optimization or kernel evolution. And then third phase, classical post-processing. Here, the classical processor interprets the quantum results. Here, classical processor, comes into picture again. Initially, in the data preparation, classical processor prepares the data, and then in the third phase, this classical processor interprets the quantum results and updates the parameters or complete additional computations. It while this processor processing the data, if that require really any additional computation, it will perform. The classical processor interprets the quantum results and updates parameters or completes additional computations. Okay, coming to the fourth phase, iteration. This process is repeated iteratively, leveraging the best capabilities of each system. Right? In the first phase, data preparation, that's compatible with the quantum computation. The quantum computation, it perform the specific tasks, and then post processing, classical processor again involve and try to updates the parameters, and fourth one is iteration. This is the major components, and it's a loop, a feedback loop between classical processor and the quantum processor. It's a classical processor and the quantum processor. Okay, yeah. Coming to here, I'm going to discuss a quantum generative adversarial network, QGANs. Quantum generative adversarial networks in this key hybrid algorithms. Here, I'm going to explain target probability distribution. This is a combines quantum circuits for data generation, that's called a generator, with classical adversarial networks discriminator. Here, our target is P0 is equal to 0.4, P1 is equal to 0.6. In generally, probability is one value, right? I mean 0 plus 0.4 plus 0.6, right? This is a 1. Now, the goal is for the quantum generator to produce a distribution Pgen that matches P target. This is our target. Now, we are going to take some values for the Pgen, and then we are trying to match these Pgen and P target, while a classical discriminator distinguishes between the two. Next, coming to here, we are going to discuss, these are the completely mathematics, key components. Here in this algorithm, QGen, okay, quantum generative adversarial networks. In this we have a 3 key components. First one is the quantum generator, classical discriminator, adversarial learning. Right, coming to the quantum generator, this quantum generator creates a quantum state using a parameterized quantum circuit. This is the formula. Cos theta of 0 plus sin theta of 1. Okay. After measurement, the probabilities of each outcome are Pgen. See, by using this formula only, gen means generator, quantum generator, Pgen. We are trying to match the Pgen with the P target. See, P0 or P0 is equal to cos square theta, P1 is equal to sin square theta. Okay. And then second component, classical discriminator. Here the discriminator evaluates how close this P generator is to P target. It uses a cost function such as Kullback-Leibler divergence. LD is equal to minus sigma I P target of I log P gen of I. This is the This is the discriminator. Here we are using the divergence for the discriminator. It's again a classical discriminator. That's the reason we are using the divergence. Divergence thing. Minus sigma I p target of I log p gen of I. And then adversarial learning. Right? In this adversarial learning, the generator tries to minimize the difference between p gen and p target. The discriminator tries to maximize it. In general, in the machine learning, we are trying to reduce the error. Error is nothing but actual minus predicted. Like that only here as well. Right? In the machine learning, yeah, what we can do, we have to reduce the error. Okay, how we can calculate the error? Error is nothing but actual minus predicted. Here also we did like that. I mean, the generator tries to minimize the difference between P generator and the P target. The discriminator tries to maximize it. Coming to here, we are going to, okay, start the algorithm, key hybrid algorithm, the QGen. First one, initialize parameters. Initial guess 0.5. I mean, theta is equal to 0.5. Define P target, P0 is equal to 0.4, P1 is equal to 0.6. Coming to first one, quantum generator. In this, we have that one P naught or P0 is equal to cos square theta, where theta is nothing but a 0.5. Cos square 0.5, P1 is equal to sin square 0.5. Computational probability. After this, these are the values. P0 is equal to 0.8776, P1 is equal to 0.111224. And then, yeah, this is the discriminator loss, that one, divergence theorem, that minus sigma pi, that one, right? 0.4 into 0.8776 into 0.6 into log 0.1224, right? This is the P0, this is the P1, right? This the P0 is the 0.4 and this one is the 0.6 initial values, this one. So LD is equal to 1 point, after calculation of this one, 1.3166. Right? I'm not mentioning any log value and all, right? You already having the idea about this. Discriminator loss, right? This is a quantum generator. This is the discriminator loss. I mean, this one, classical discriminator. We completed this step and this step. Now, we are going to update the generator parameters. See, yeah, how we can update? See, this is the updation. Just like updation of bias and weight in the back propagation or any neural network. You all know that. Theta is equal to theta minus eta into dou LD by dou theta. What is dou LD? Dou theta. It's the generator uses the gradient of the loss to adjust theta. See, this is the formula. Dou LD by dou theta is equal to minus sigma P target of I into dou by dou theta of log P gen of I. Right? P gen, we know that cos square theta, sin square theta. So dou cos square theta, dou theta, this is the thing. Update theta, this one. Okay, it's again a full of mathematics. And now we are trying to repeat the step 2 to 4 until P gen closely matches the P target, just like a back propagation. Right? Just now I mentioned that one, right? In the back propagation, what we can do? I mean, we all know, you all know something about machine learning, right? For that machine learning, back propagation is one of the basic thing in the back propagation. Yeah, from I'm start with the initial node. I mean input layer, hidden layer, output layer. Okay, I pass something from the input layer and we perform some operation in the hidden layer. Yeah, sure. See, here we have a 3 steps: quantum generator, classical discriminator, adversarial learning. In this quantum generator, we are going to measure the P gen, that's called P naught P1. In the classical discriminator, we are going to calculate the divergence, and then we repeat that thing. I mean, we have to minimize the difference between P gen and P target, just like a back propagation thing, right? Coming to the back propagation thing, what I am going to tell you, repeat step 2 to 4 until Pgen closely matches the P target, right? Yeah, Pgen closely matches to the P target. In this, as like the back propagation one, here also we have to repeat the steps until our Pgen closely matches the P target. Okay, in that back propagation, in generally by updating the weight and bias, we are going to recalculate the everything until our actual one, I mean predicted one, matches with the target one. Like that also, here we are going to repeat the steps 2 to 4 until Pgen closely matches to the P target. Okay. Yeah. Coming to the convergence. Here, our iterations, the quantum generator adjusts theta such that Pgen is equal to P target. Okay. Now, this is the benefits of hybrid models. Enhanced performance, scalability, adaptability, feasibility. These are the benefits of hybrid models. We'll get back to here after completion of some case study here. See, this is the example. This is the example. Here I'm going to, yeah, previously that is the algorithm. Then I'm going to give, I'm going to explain. Yeah, Qgens for financial data modeling. I'll show you one Python example. Okay, yeah, you don't worry. Yeah, Qgens for financial data modeling. Here, generate synthetic financial data that mimic the statistical properties of historical market data for risk analysis and stress testing. Here, see, historical data. This is a historical data. Minus 0.02, 0.01, 0.03, minus 0.01, 0.02. These represent daily percentage changes in stock prices. These are the daily percentage changes in stock prices. Our goal is generate synthetic data or synthetic that matches the statistical properties mean, variance, skewness, correlation of or historical. Our goal is, yeah, generate synthetic data that matches the statistical properties mean, variance, skewness, correlations of or historical. See here again, we have to prepare the historical data. See, pre-process the data. First one, what we can do here, we are going to pre-process the data. Normalize the historical returns to ensure they fall within a range compatible with quantum circuit outputs. See, normalize the historical returns. It is not a new one. It's again a normalization technique. In generally, we have two techniques. First one is the min-max normalization. Second one is the Z-score normalization. Here we are using the min-max normalization. We are using the min-max normalization, right? In generally, min-max normalization as the formula present value minus, okay, minus min by max minus min. That's a simple formula, but yeah, okay, R historical minus this is the values. These are the historical values, and after applying that particular min max normalization, our historical values transformed like this, 0.2 so and so. Okay, and then these are the statistical properties: mean, variance. These properties guide the evaluation of synthetic data, right? Pre-process historical data, right? I repeat again, this is a synthetic data. We have to generate a synthetic data based on that matches the historical properties of our historical. We have a historical data. Based on that historical data, we are going to generate a synthetic data that matches with the historical one. I mean mean, variance, skewness, correlation. Yeah. Coming to further preparation, initially we need to pre-process the data. I mean, we are taking the historical data and then normalize it. Okay, normalize the historical returns to ensure they fall within a range compatible with quantum circuit outputs. Quantum circuit outputs. Compatible with quantum circuit outputs. Okay, and then extract statistical properties mean variance here, right? Yeah. Next quantum generator. Here quantum circuit. Create a parameterized quantum circuit with rotations and entanglement gate to represent financial data distributions. A qubit circuit is used to generate two-dimensional data. Yeah, and then quantum probability distribution. The quantum circuit output probability distribution, Pn, over possible synthetic return after measurement. And then classical discriminator. This is a classical discriminator. Yeah. See, I'll get back to that steps. After multiple iterations, okay, Pgen closely matches P historical and synthetic data. R synthetic becomes indistinguishable from a real data. See, after completion of that all the steps, what we read it here. See, what are the steps? These all steps. After completion of these all steps, okay, we got this particular synthetic data. This, yeah, now this synthetic data comparing with the actual data, yeah, it is same pattern in the historical data. First one is the negative, second two values are positives, fourth one is the negative, last one is the positive. So these mimic the properties of our historical. So after these all the steps, synthetic data is similar to that historical one. So this will help us to estimate the stock market. Here what we mentioned here, right? Generate synthetic financial data that mimic the statistical properties of historical market data for risk analysis and stress testing. Yeah. In addition to, yeah, that is one of the case study. Here I am another case study is assisted drug discovery. This is another case study. Okay, in this case study, identifying potential drug candidates by analyzing molecular interactions and energy landscapes. Here, hybrid approach. Pre-process molecular data and reduce the problem size using clustering techniques. Here we pre-process the molecular data and reduce the problem size using clustering techniques. Handle post-processing such as verifying molecular stability. And then coming to the quantum component, use quantum variation algorithms like VQ to compute molecular ground states, which helps determine binding affinity between drug molecules and target proteins. It again yeah, we need some chemical knowledge here. Yeah, that we need to determine the binding affinity between the drug molecules and target proteins. And feedback loop, it repeat, I mean classical optimizers iteratively refine the parameters of quantum circuit to improve precision in energy calculations. And then accelerated the discovery of potential drug candidates for disease like Alzheimer's. That is the outcome. Okay. And then, yeah, coming to our programming wise, I mean, cloud-based hybrid quantum computing solution for researchers and industries. Future prospects. See, we need to spend some time on this particular concept. Naively speaking, hybrid means we all know that, right? A program that runs both classical and quantum code. Hybrid means a program that runs both classical and quantum code. Yeah, here a quantum code is defined as a sequence of quantum gates that you apply to one or more qubits on a quantum device or a quantum processing unit called QPU. QPU. Just like a CPU, it's a QPU, quantum processing unit. Classical refers to a program that runs on a CPU, regular computer, written in any programming language. See, that's a we are hybrid. It's a program runs both classical and quantum code. Quantum code here is defined as a sequence of quantum gates that you apply to one or more qubits on a quantum device or a quantum processing unit QPU. And classical refers to, we know that a regular program. Typically, you would choose one that can easily interface with a quantum computing service. While, see, I'll show you one diagram. See, this one. I'll get back to that slides. See, here, this is a classical computer. This is a QPU. Yeah, this one program, this is the cloud-based hybrid. This is going to work. It's a future one actually. A simple model for accessing a quantum processing unit, QPU in the cloud. My computer, it is a classical one. That's called a quantum circuit. Yeah, classical programs are running in the local computer. If you want any quantum one, then we'll send it to quantum cloud service. That will be considered as a job. That job run by the QPU. That after completion of that process, QPU return the result to the quantum cloud service. Quantum cloud service return back to the my computer. See, now get back to our discussion. See here. While the might seem straightforward, there is more than one way to turn a quantum program into a hybrid one. Now, a simplest way to do this is to run classical part on your computer and submit the quantum part to a quantum cloud service. Okay. Typically, such a program will define a parameterized quantum circuit that is executed on a quantum processor. See, such a program will define parameterized quantum circuit that is executed on a quantum processor in a classical optimization loop. This means that each iteration in the loop will specify a different set of parameters that are passed to the parameterized quantum circuit, generating a new standalone quantum circuit. Right now, that classical part will be running in our computer and submit the quantum part to a quantum cloud service. That typically such a program will define a parameterized quantum circuit that is executed on a quantum processor in a classical optimization loop. Right? This means that each iteration in the loop will specify a different set of parameters that are passed to the parameterized quantum circuit, generating a new standalone quantum circuit. See, if you have given this mode of operation a try, you have probably found that the unit of work is typically referred to as a job. This cloud service, whenever we need a quantum computing thing, this classical computer will send the request to the cloud service. Cloud service prepare a job that will be transfer to the or send a request to the QPU. That the unit of work is typically referred to as a job. Each job gets created when you submit a quantum circuit and is associated with a result. Once we send the request, this quantum cloud service waiting for a result associated with a result. It expects a result that contains the qubit measurements data. This quantum cloud service prepare a job and send it to QPU. QPU will perform the operation. After that, it will return the result in the form of qubit measurements. If you submit multiple jobs as a part of your hybrid program, then you get back multiple results. That's in generally happens. That in generally happens, right? Another thing you might have noticed is that this type of workflow generates a lot of jobs. Each job is added to a queue. In general processing, we have a multiple jobs. We have to add that all the jobs in a queue. Yeah, right. These all things will happen. Okay, quantum. This is a quantum circuit. This is a classical computer. This is a QPU. Right. If your unit of work is no longer a single circuit but a program that generates circuits, this means that your hybrid execution model can benefit from a more integrated approach. Okay. Yeah. Now, future prospects: algorithm development, quantum hardware advances, increased accessibility. See here, algorithm development. Focus on robust hybrid algorithms for broader applications, right? We need a hybrid algorithms for broader applications. Now, so many researchers are focused on this particular quantum computing, especially with these hybrid models. Right. Another is the quantum hardware advances. Improved coherence times and error correction will enhance hybrid model performance. Right. And then increased accessibility. Cloud-based hybrid quantum computing solutions for researchers and industries. Cloud-based hybrid quantum computing solutions for researchers and industries. Just now we discussed this one. Increased accessibility. Now people are thinking about this one. I mean, so many people are working on this. I took that article from the blogs. One of Microsoft researcher, wrote that one actually. Right. Yeah. Some challenges in QML. Hardware implement limitations. See, quantum decoherence. Short lifespan of qubits. This is one of the hurdle. I mean, one of the challenge. Quantum decoherence. Short lifespan of qubits. Limited number of qubits for practical applications. Limited number of qubits for practical applications. This is one of the limitation with the hardware. Without having the qubits, right? This thing is not possible. So this is one of the limitation we have to overcome. Another is the noise and error rates. Another is the noise and error rates. Even though it is going to solve a bigger problems or harder problems or complex problems, whatever, but we need a error. I mean, most of the people will expect the exact matches what they want actually. Noise intermediate or scale quantum device have high error margins. NISQ. And then algorithmic challenges. Designing quantum specific ML algorithms remains complex. Designing quantum specific ML algorithms remain complex because these algorithms need to, that quantum computer needs the input in terms of qubits. So we need to convert our regular thing into a qubits one. That is also one of the challenging tasks. Another is ethical concerns. We need to follow this particular challenge as well. Okay, I'll get back to code. Yeah, I'll share my, yeah. Yeah. Yeah, it is one of the simulator. This is one of the simulator, right? My code is visible, right? This is
Yes,
all
yes.
about, yeah, MNIST data set. Okay. Yeah. Here I'm going to creating the CNN architecture. CNN with the hybrid one. This is a hybrid. Yeah. Okay.
Sir,
Coming
can you
to
increase the size of the screen so that it will be better?
visible. Okay. Now
Yeah.
it's okay.
Yeah,
Right?
yeah. It is
Okay.
good. Thank you.
Yes. Thank you. Right. Creating the CNN architecture first for the qubits. It just like a, yeah, this qubits implemented by a this library, Penny Lane. First of all, we have to define the quantum circuit number, I mean qubits, and then this is from that particular QML device default qubits, bytes and qubits. This is their syntax, and it name as dev, just like a developer, a development, @QML dot qnode of dev. Now we are going to define this qnode. See, in our regular discussion, I am using this word entanglement. That entanglement correlates the qubits actually. Right? Initially, we have to, this is the Angel embedding inputs, bytes and qubits range of this 5. And then basic entangular layers, weights, bytes, and return QML dot exp val of QML all is bytes is equal to I for I in range of n qubits. It will apply the formula that all is bytes of I for I in range of n qubits. It's a exp value. This angel embedding layer and then basic entanglement layer, entangular layers. Angel embedding layer and basic entangular layers. Okay, coming to, yeah, this is about Q node. This is about Q node. Here we created the angel embedding inputs and the basic entangular layers, and then we are going to apply this particular formula and return that value. Okay, with this n qubits, and then define the Q layer. Define the Q layer. Here n layers is equal to 3 and the weight spaces is equal to weights n layers n qubits. Okay, now coming to, this is about number of layers and weight shapes. N layers and n qubits. I mean, here we have 3 layers and 5 qubits. Now this is about CNN, simple CNN architecture. This is a simple CNN architecture. We all know that CNN is CNN, convolutional neural network. This convolutional neural network, we have a convolutional layer, and that in that convolutional, we have some kernels, strides, okay, pooling layers, okay, flatten layers, okay, etc., etc. Right? Yeah, this is basically for image processing. Yeah, this program is also for the classification of digits, 0 to 9 digits. Okay, MNIST. Right? Yeah. Yeah. Here first one, class net NN module, and this is a init. This is a init method. I mean, we all know that it's a constructor, right? It's a class, it's a constructor, and then super of net self init. I think no need to explain this one. Our actual thing is starts from this particular line. Here what we can do, this is a convolutional layer, one with one input channels for grayscale images. 16 output channels and 5 by 5 kernel. Here for that NN conv 2D of 1 channel, 16 output channels, 5, yeah. Okay, 5 by 5 kernel, and stride is equal to 1 and padding is equal to 2. Right? Yeah. Padding is equal to 2. After this convolutional layer, we have a batch normalization. See, self dot bn1 is equal to nn dot batch norm 2D of 16. And then after that, max pooling layer. This is a one set. Convolutional layer, batch normalization, max pooling. And then second set. Second set. Okay, convolutional layer, batch normalization. After that, our quantum layer will come into the picture. See, it is very, very important, right? Q node. What is Q node? This one is a Q node, right? This is the Q node. Yeah. Self dot Q layer 1. We have a four quantum layers. We have 2 CNN layers and 4 quantum layers. Self dot Q layer 1, Q layer 2, Q layer 3, Q layer 4. In this QML dot QNN dot torch layer of Q node, what we created earlier. And weight shapes. Here weight shapes is equal to this one. N layers and qubits. 3, 5. Okay. Q layer 1, Q layer 2, Q layer 3, Q layer 4. Okay, with the Q node, Q node, Q node, Q node. After that, we have a 3 fully connected layers. FC1, FC2, FC3. In that linear 32, 7 by 7, 120, 120, 20, 20, 10. These are the parameters. Fully connected layers. Fully connected layer means we have a connection with each of the node in the previous layer having the connection with the each of the node in the next layer. That's called a fully connected layer. FC1, NN linear, 32, so and so. This is the full connected layers. This is the quantum layers. These are the CNN layers. Yeah, CNN layer 1, CNN layer 2, and quantum layers, fully connected layers. And then this is a constructor. And then forward. Now propagate the input through the CNN layers. For that, X is equal to self dot pool of F dot ReLU. Here ReLU is a activation function. Self of Bn1 of self dot con1 of X. We have to pass this X. This is the input actually. Self dot con1 of X. Okay, convolutional 1. This one I'm talking conv1. Okay, this is the and then conv2 and mean convolutional operation conv1, conv2 of X. And then flatten the output from the convolutional layers like this. I mean just like a reshape, flatten. X is equal to X dot V of minus 1 comma 32 into 7 by 7. Okay, in this we have a C, this one. 32, 7 by 7. Pass the output to the quantum layer. Now F dot ReLU, self of FC1 of X and then FC2 of X. Pass the output to the quantum layer. And then we are going to split the data into these 4 portions: X1, X2, X3, X4, torch. Here torch is a library actually. Yeah, torch for the neural network. Torch split this input, comma 5, comma dimensions is equal to 1. Next, this Q1 will be given as input to Q layer 1, Q2, Q layer 2, Q3, Q layer 3, and Q4, Q layer 4. And then torch cat of categorical. I mean categorize x1, x2, x3, x4, axis is equal to 1. And then this input will be given as input to the FC3, fully connected. FC3 of x, return x. This is the way of constructing the network of this particular hybrid model. With hybrid here, we are combining CNN with this Q node. I mean Q node, quantum circuit. Okay, and then yeah, and then train the CNN. The CNN model is initialized. The loss function and optimizer are set up, and data loaders for training and validation data are created. The training loop iterates through the data set for a specified number of epochs, performing forward and backward passes to update the model's parameters. The model is initiated, the loss function and optimizers are set up, and data loaders for training and validation data are created. The training loop iterates through dataset for a specified number of epochs, performing forward and backward passes to update the model's parameters. See, here we created downloaded the data sets for train data, test data. Data sets, MNIST, root data, train true, transform to tensor, right? We all know that scalar, vector, tensor. It's a tensor data. Okay, here we are using the tensor flow, right? See here, if suppose CODA is available, we are going to use that CODA. If you use CODA L CPU, just like we are right leg here. Okay, the torch vision. Yeah, this is a torch vision, and that from this torch vision we are using the transforms data sets, a tensor also from the torch vision. It's a torch vision is a software for vision, just like a computer vision, CV2 or OpenCV, right? OpenCV. Okay. Yeah. Now we are going to prepare the data set. I mean, download the data set from MNIST for the train data. Download true, and test data. Data sets MNIST root data. Train false. This is training is not required. Transform to tensor. I mean, it is internally created for the training. It is not created for the training. Just like that. Okay. This is the train data and test data. Now, yeah, it is Google Colab is efficient. I mean, sufficient. We'll check it. Actually, yeah, because here we are using the CODA, right? I mean, even it is for the CPU, right? Yeah, Colab is working well. Okay, and coming to train the model. Right, we already discussed this particular thing, right? The training is data loaders for training and validation data are created. The training loop iterates to the data set for a specified number of epochs, performing forward and backward passes to update the model's parameters. Now we created the object here. Initialize our CNN model. We prepared the CNN model by with the class name net, right? Yeah, coming to data set, it's a train data. We already downloaded this one. Now criteria, this is the criteria. This is our cross entropy loss for classification, and then after that optimizer, it's a stochastic gradient descent optimizer, SGD, stochastic gradient descent optimizer. Okay, yeah. In this we are using the torch.optim.sgd of CNN dot parameters. CNN dot parameters. Yeah, CNN dot parameters. It assign. Yeah, this is a parameters thing, and this is a learning rate. LR is equal to 0.001 and momentum is equal to 0.9. Okay. Yeah, this learning rate, based on that learning rate, it is going to learn, I mean, how much it have to extract the data from the given input. I mean, suppose it's a here our input is a image, so it is going to extract the information from the image. And your train size, split the data into training and validation sets. We all know that, right? Yeah, in generally for the train data, we have to split into two categories. One is for training, another is the validation. After successful completion of training our model, we have to validate the model with our known data. After that, we have to compare the accuracy of training data and the validation data. Validation is nothing but it's not a testing, because we know the outputs, right? We know the output labels. Train size is equal to int of 0.8 into length of data set. I mean 80% is for training, 20% is for validation. Train set, comma, val set is equal to torch utils data random split data set, comma, train size, comma, length of data set, comma, train size. I mean 80% is for the train set, 20% is for validation set. Next, train loader. Now we are going to load the training data. Train set, batch size is equal to 4, SAPL is equal to true. SAPL is equal to true. And then number of epochs, 10. Right? Yeah, we all know that, right? These parameters, SAPL. I mean here random split. I mean it is randomly split the data set into train set, training portion, as well as validation portion. Randomly it have to take the entries from the data set and assign it to the training set, and then later it will assign to the validation set. I mean 80% is for training set randomly and validation, and 20% is for validation. And then number of epochs is equal to 10. We all know that we have to repeat the model of 10 times. It's a epoch in range of num epochs. And then now CT, some epoch so and so, running glass 00. Now train loader. This is a train loader. I mean, this is all about training data set. Now inputs, comma, we enumerate the train loader, I and comma data. Inputs, comma, labels. Inputs, comma, labels. And then 0, the parameter gradients to avoid accumulation. Optimizer dot 0 grad. Optimizer dot, this is a 0 the parameter gradients to avoid accumulation. Next, outputs is equal to CNN of inputs. From that inputs, comma, labels, we are going to give inputs as a inputs to the CNN. Forward pass. We are going to pass these inputs to the our created model here. Right? And then outputs. Now compute the loss by passing these labels. We already know the labels, and then it returns the labels. Criterion loss is equal to criterions of outputs, comma, labels. Compute the loss, and then that loss will be back propagated backward. Loss dot backward. This is called a back propagation. Loss dot backward. Based on this particular thing, we are going to pass this particular thing to the backward. That's called, I just discussed that one, right? Back propagation. Error is nothing but a actual minus predicted. Actual minus predicted. Based on that particular loss thing, loss value, we are going to propagate to the error to the backward. Based on that error, we are going to recalculate the weight and bias, and updated that weight and bias, Okay, last dot, this particular last dot backward, back propagation. Okay, we have to recalculate the weight and bias. I mean, update the bias and bias and weight, and recalculate the, I mean, reapply the process and try to calculate the everything. And then again calculate the loss. This process will repeats until we reaches our target value. And then optimizer dot step update the model parameters. Okay, update the model parameters, and this is a finished the training. And then this is all about train the CNN and evaluating the model. Now set the model to evaluation mode. Use it to make predictions on the validation data set and calculate the accuracy of the model. Okay, calculate the accuracy of the model. Here, again, CNN dot evaluation and with the torch, no gradients. For data in val loader, images, comma labels, just like previous. Outputs is equal to CNN images, and then CNN of images. Predicted is equal to torch dot max of outputs dot data, comma 1, and total is equal to total plus 1 labels dot size of 0, and correction is correct is equal to correct plus predicted is equal to labels. This is the sum of the particular thing, and accuracy on the validation set. Correct by total. Yeah, for the calculation of this particular accuracy, we performed these two things here. Okay. Yeah. This is a image class hybrid. Yeah. CNN with CNN and quantum thing. Quantum circuit one. Okay. Now get back to our PPT. Yeah. See. Yeah. These are the hardwares currently: IBM Quantum, Google Sycomore, and D-Wave systems. And challenges: decoherence, error correction, qubit scalability. See, these are the challenges now actually. These
Sir,
are the
your screen is not visible.
Yeah. Hello?
Yes, sir. Your PPT is not visible, sir.
Yeah. I'll share it.
Yes, sir. Now.
Okay. Some of you are asked about that question, right? How we can implement fault tolerance, quantum computing. Yeah. Now, bigger organizations like IBM, Google are spending much more money on that actually. Yeah. I am also a beginner for this particular quantum computing. Yeah. This is the I'll show you. See here, IBM, Quantum, Google Sycomore, 53 qubit, and D-Wave systems. Yeah, challenges. These are the challenges: decoherence, error correction, qubit scalability. Right? These are the challenges. Even Indian government also. Yeah, I think before last year, 4,000 crores are announced for research related to this quantum computing. I think I heard about that news in newspaper or somewhere else actually, because it's one of the as like a supercomputer. Now people will spend more time, more money on this quantum computing. More research is going on actually. Yeah. right? What I shown here, right? That particular willow, that is, I think it's a three days back news actually. Right, it solved the problem, that particular problem what I shown, right? Yeah. Okay. These are the some challenges. I mean, hardware wise. Yeah. There are the decoherence, error correction, qubit scalability. Yeah, it's a it's a 10x or 100x, even 1000x speed compared to classical computers. What we used, I mean, what we are using current days, even though it's a running in GPUs, TPUs, right? But some lag is there, some challenges are there, like this decoherence, error correction, qubit scalability, lifetime of that qubit, right? Yeah. Okay. Yeah, this is all about today's talk, madam. Thank you.
Thank you, sir. Participants, if any questions are there, you can write in the chat box so that sir will answer. Sir, can we execute that code in the Google Colab itself?
Yeah, I'll try it, but maybe it will take some time actually.
Okay.
That's the reason actually. Yeah, I'll share it to you. Maybe you'll send the code to these guys. Maybe they will try in their college.
Yeah,
Yes.
please share the resources, sir, so that
Yes.
I will share with all the participants. It will be
Yes. Okay. Thank you.
Thank you, sir. So thank you so much. It's a combination of hybrid, means quantum, classical and quantum machine learning. You have explained clearly and with the practical implementation. Thank you so much for your time and contribution for this FDP, sir.
Yeah. Thank you. Thank you very much. Thank you, one and all. Yeah. Can I leave, madam?
Yes, sir.
Thank you. Thank you very much.
Participants, please fill up the feedback form for this session. And I'll try to start the next session within 5 minutes. You can take the break for 5 minutes. Participants, don't leave. The next resource person is here in the meeting. I'll be starting soon, so don't leave the meeting. I'm just giving a break of 2 minutes. Hello, Mr. Dhanshekar. You can unmute yourself, right? I made you the co-host, so you can try to unmute yourself.
Can you hear me now?
Yes.
Hi.
Yeah,
Hi. Yeah.
hi. Just 2 minutes, we'll start the session because it's a continuous session. I've given just a break of 2 minutes.
Yeah. Sure. No worries. Yeah.